In this video, we are going to learn the experiment AM and FM spectrum by using spectrum analyzer. The objective of this experiment is to observe AM and FM spectrum on spectrum analyzer. Through this video, we are also going to learn how to use the spectrum analyzer instrument. In this experiment, we are going to use two instruments. First one is arbitrary function generator used in the lab. This function generator is used to generate AM and FM signal. To see the spectrum, we are going to use the device spectrum analyzer. This is to see the spectrum of AM and FM signal. Okay, so we divide the experiment into two parts. Part A is to see the AM spectrum. So let us see what is AM signal, which is going to be generated by the function generator. So AM signal, which is going to be generated by function generator. So we have to insert various parameters in the function generator, and it generates waveform which is of this kind. So basically this is the AM equation. It is A by 4.4 1 plus m by 100 sine 2 pi fmt sine 2 pi fct, where A is the carrier amplitude. We can also call it carrier amplitude before modulation, and m% we are going to give modulation index, or we also call it modulation depth in percentage. FM is the message, or we also call it AM frequency, and FC is the carrier frequency. So these are the parameters that we are going to give in the function generator. If you see, here is the message signal is of sinusoid. So basically this is a type of tone modulation, and more specifically we can call it single tone modulation. Okay, so let's rewrite the AM equation. We want to do the theoretical calculation of this AM equation. So basically this is our AM equation. On expanding, we can get the equation which has two terms. So if you can see, this is the our carrier term, which does not include the message, and this is basically our DSP SC signal. So as we know that conventional AM is DSP SC plus carrier. So again, writing the formula of sin A sin B, we can break this term again into two parts. So this part we can break into two, that is the first part, and this is the second part. So this is just the trigonometric identity that we can use here, and so we can get our final that equation, which contains of three terms. The first term is carrier itself, and the second term, if you see, this is the term which is present at frequency Fc minus Fm, so we can call it LSB, and the third term which is at FC plus FM, so we are going to call it USB, where LSB is the lower sideband and USB is the upper sideband. So if you take this amplitude inside this bracket, so we can, the final equation is of this kind. So we can see the lower sideband amplitude is this much, A into modulation index percentage divided by 8.8, and the USB amplitude is A into modulation index in percentage form divided by 8.8, and this is A by 4.4. Now calculate the carrier power, sideband power for this equation. So if you see the carrier power, so you have to see the carrier term. So this is the carrier term whose amplitude is A by 4.4. So the carrier power can be written as RMS value, which is going to be A by 4.4, since this is the peak amplitude. So this is A by 4.4 into 1 by root 2, because we are going to convert into RMS value. So this has to be square, and we have to divide it by the resistance. If you see the resistance value, so we are going to use the resistance of the spectrum analyzer, which is typically of 50 ohm in our spectrum analyzer. So basically this is the carrier power which is there in our equation. So to calculate the LSB power and USB power, so if you see that LSB amplitude and USB amplitude, both are same. So these two powers are equal. So if you see we have to use the power formula. That power formula, again, this is the power, which is the RMS square upon the resistance. This RMS it is in voltage form. So again, rewriting the same thing, this is the amplitude into ampersand divided by 8.8. We have to convert it into RMS value, so it must be this, and to make it a square, then divide by resistance. So these two powers are same, so let's call it carrier power PC. Let's call it this PLSB, and which is equal to PUSB. So this is the term that if you see the total sideband power, so we are going to add this two component. So the total sideband power, let's denote it by PSB, which is equal to PLSB plus PUSB. So this is the total sideband power. So if you see the AM wave whose total power can be calculated as, this is PC plus PSB, and PSB is for PLSB plus PUSB. Now let us see the power spectrum, the equation which we have derived. So this is basically, we are going to plot power spectrum. So this is basically power versus frequency. So if you can see, this is the frequency axis and this is my power. So if you see the equation which we have derived here, this is basically the carrier term which is present at frequency FC. So let's denote it by FC, and this is my upper sideband which is present at FC plus FM, and this is the lower sideband which is present at FC minus FM. So since this is a power, so we were just going to write the power of each. So these are the three impulses which we are going to get from this equation. So the power at USB that we have derived in the previous slide, which is A into ampersand divided by 8.8. Sorry, this is 1 by root 2, then square divided by R, and this is the amplitude, this is the power of carrier which is A by 4.4 into 1 by root 2 square upon R, and this is the same as this one, so we just have to copy this value. This is the A into m% divided by 8.8 into 1 by root 2 square upon R. So this is the power spectrum that we should get in the spectrum analyzer when we place the value of A, M and R. Now let us set the some cases so that we can verify our theoretical values with the practical values. So this is the parameters that we have to insert in the function generator to generate AM signal. So we have to put the value of A. Let us see, this is 2.2 volt. This A value is. We set our carrier frequency at 400 kilohertz, which is the carrier frequency, and the message frequency. This is my AM frequency. This is the 5 kilohertz, and the resistance that is equal to 50 ohm we are going to take for our calculation. So we are going to calculate the powers for different modulation index. If you see, this is the first case that we are taking modulation index, which is 50%. This is my under modulation case. This is my under modulation. Second is the 100%, and which is nothing but exact modulation. So this is my exact modulation case, and third case that we are going to see is over modulation case. So this is my over modulation case. If you observe the carrier power that we are going to calculate, we can calculate it from this. This is the A value, which is we have taken 2.2 volt. So if you calculate this value, and when you plug this value 50 ohm, so we get the value of nearly 2.5 milliwatt. So this is 2.5 milliwatt. If you observe the different modulation index, since this carrier power term does not include modulation index in its formula, so it is independent of the modulation index. So in all three cases we are going to see that is carrier power is 2.5 milliwatt, and this is also same. This is also 2.5 milliwatt. Okay, so if you calculate the lower sideband power for this three different modulation scheme, so we have to use these formulas. So this is my basically USB, and this is my basically LSB powers. So for let's see the first case, which is 50%. So if you take modulation index 50%, the first case, A is 2.2, R is 50. So we get the value of lower sideband and upper sideband, which is equal to 156 microwatt. If you take the second case, which is the 100 modulation case, so again we have to put these values in this formula, make it 100%. All other values are same. In this case we are going to see this is 625 microwatt, and in the third case, which is 120%, we are going to see this is going to be 900 microwatt. If you see this total sideband power, as we know, this is nothing but PLSB plus PUSB, so it is just the twice of these values. So this is equal to 312 microwatt. This is 1250 microwatt, and this is 1800 microwatt. Now if you see the bandwidth related things, so I have already written these values. So this is 400 kilohertz center frequency, which is the carrier frequency. So since we set the values carrier frequency 400 kilohertz, so we get an impulse which is at 400 kilohertz, and the upper sideband value is 405 kilohertz because we set the FM frequency 5 kilohertz, and the lower sideband frequency is FC minus FM, which is nothing but 400 minus 5 kilohertz, which is 395 kilohertz. And this is the bandwidth. We can see this is nearly 10 kilohertz, which is nothing but the twice of FM. So this is a complete theoretical analysis of this experiment for AM. So now let's see the spectrum practically. So this is our setup, this is my function generator, and this is our spectrum analyzer. So let's generate the AM signal by this function generator. So this is the modulation button, and you can set this frequency 400 kilohertz. It is already set there. This is my carrier frequency, which is at 400 kilohertz. This is the amplitude, that is the A in our equation, that is 2.2 volt peak to peak. And the AM frequency, which is nothing but the modulating signal frequency, this is 5 kilohertz we set, and the first modulation index for which we are going to calculate the we are going to see the spectrum, that is modulation index 50%. So let's turn so this is the AM waveform which has been generated by this function generator. So to see the spectrum on a spectrum analyzer, we have to first set the frequency span, and this is my frequency span, and we can set the center frequency at 400 kilohertz. So this is my 400 kilohertz. The span is, if you can see, the span is 50 kilohertz. So the whole screen is 50 kilohertz, and the center at 400 kilohertz. So if you see the marker, we can measure this center frequency, which is at 400 kilohertz. You can see the reading at this marker reading is 400 kilohertz, and the power which is associated with this carrier frequency is 2.46. If you see the theoretical values, so we have calculated this as 2.5 milliwatt for 50% modulation index, and practically we are getting 2.46 milliwatt. So this is the we have verified the practically also. So now if you see the if you change the marker to next peak, let's say the right next peak, this is my upper sideband. You can see the frequency is 405 kilohertz, and the power associated with this sideband is 154 microwatt around. So this is the calculated theoretical value for the upper sideband. This is 156 nearly microwatt, and we are getting nearly 154 microwatt. If you check the lower sideband, so this is the impulse which is appearing at 395 kilohertz. So this is just the FC minus FM, because we set FC 400 and 5 kilohertz to modulating frequency. So this is at 395 kilohertz FC minus FM, and the power associated with this is also nearly 153 microwatt. So this is the spectrum we can see practically. And so now we are going to change the depth to 100%, which is 50% in the previous case. So let's change the depth to 100%. So this is 100%. Now this is the second case that we are generating the signal, which is 400 kilohertz FC, amplitude 212 volt peak to peak, 5 kilohertz. This was the earlier values, and depth we have changed to 100%. So if you see the spectrum now, because since we have not changed the frequencies, so the impulses are at the same frequency levels. So but the amplitude, you can see it changes, it gets changed. So if you see the lower sideband, which is the marker reading, it shows 395 kilohertz and 609 microwatt. So nearly it is 610 microwatt, and if you see the theoretical values, it is what, nearly 625 microwatt, and practically we are achieving this value nearly 613 microwatt. If you see that carrier power does not change by changing the modulation index, so this is the same as previous, nearly 2.46 microwatt milliwatt. So this is 2.46 milliwatt.
काटना ही है तो
Now we are going to see the third case, where we are going to take the over modulation case. So let's change the depth to 120%. This is the maximum depth you can set in the function generator. So this is the 120% modulation index. Now you can see that we have changed the depth to 120%. Now let us see the spectrum. Again, we have not changed any frequency term, so it is not going to change the frequency levels. But if you see that sideband power has increased its level, so if you see the carrier power, the first one, this is around 2.46 milliwatt, which was the earlier result, because it does not depend on the modulation index. If you see the upper sideband values, so this is my upper sideband, which is nearly at 881 microwatt, and the values we got in the third case is the 120%, and this is the lower sideband and upper sideband, which is equal power, which is around 900 microwatt, and in the spectrum analyzer we can see this is nearly 888 microwatt. Now we have the theoretical as well as practical values with us. So now we can compare them and we can conclude the experiment. So if you see the carrier power, which is theoretically 2.5 milliwatt, and the carrier power which was practically measured was 2.46 milliwatt. So in all three cases we are getting the observed as well as theoretical values, and the lower sideband is also approximately they are same. This is the lower sideband and upper sideband powers. This is 625 in the second case, and we are getting 613 microwatt practically. Third case also this is 900, and we are getting nearly 880 microwatt. So if you observe this, the modulation index, when we increase the power, carrier power is same, the carrier power is, this is same values, they are not changing with the modulation index, and the sideband power, that is lower sideband and this sidebands, they are getting changed and they are actually increasing with the increasing value of modulation index. So if you see, we can write the conclusion that if you increase the modulation index, this increases the sideband power, and the carrier power, if you change this, change this modulation index, carrier power does not change, it remains the same. So the carrier power is independent of modulation index. So if you see the frequency, so when you increase the message frequency or decrease it, it changes the bandwidth. So if you increase the message frequency, the bandwidth of the system gets increased, but changing the frequency, it does not contribute anything. It does not contribute anything to the power. So it just related to the bandwidth, to the power. And since this is the first, we have seen this is the modulation index that we are increasing, so sideband power is increasing, PC does not change, but the total power, if you see, it is going to increase because of the sideband power is increasing. So this is going to increase if you increase the sideband power.